In the previous lecture, we discussed the Eulerian coordinate system and the Lagrangian coordinate system. Now in this lecture, we will make a relationship between the derivatives in these two coordinate systems. Suppose that we are given a fluid property alpha. As seen in the Eulerian coordinate system, we know that this property is a field variable that depends on the space coordinates x, y, z and the time t. But in the Lagrangian coordinate system, we have to follow the motion of a fluid element, and we determine how alpha changes as a function of time t as this fluid element flows. So in this case, the space coordinates x, y, z are no longer independent variables. Instead, they depend on the time t. So, as seen in the Lagrangian coordinate system, the fluid property alpha is given as the function of x of t, y of t, z of t and the time t. Since the expression on the right hand side is a function of time t only, therefore in the Lagrangian coordinate system, the fluid property alpha is given as the function of time t only. This is what we have already discussed in the previous lecture. Now we will find the change in the value of alpha for some period of time delta t. First we will find this change in the Lagrangian coordinate system, and then we find the same change in the Eulerian coordinate system. So let me first calculate it for the Lagrangian coordinate system. Suppose that at some time t, the fluid element was at this position whose coordinates are x, y and z. Let me follow the motion of the fluid element for time delta t. Suppose that after time delta t, the fluid particle reaches at this point whose coordinates are x plus delta x, that is change in its x position is delta x. And similarly, suppose that the change in the y position is delta y, so the y coordinate of this point is y plus delta y. Similarly, the z coordinate is z plus delta z. The value of alpha at this point is alpha of t, and the value of alpha at this point is alpha of t plus delta t. Okay, so the change in the value of alpha as seen in the Lagrangian coordinate system is alpha of t plus delta t minus alpha of t. In the Eulerian coordinate system, we have to find out the change in the value of alpha at these 2 points. Note that in the Lagrangian description, the particle was at this point at the time t. Therefore, in the Eulerian description, we have to consider the value of alpha that depends on x, y, z and the time t. Similarly, in the Lagrangian description, after time delta t, the particle was at this point whose coordinates are this. Therefore, the value of alpha that we have to consider at this point is alpha of x plus delta x, y plus delta y, z plus delta z and t plus delta t. So the change in value of alpha at these 2 points is alpha of x plus delta x, y plus delta y, z plus delta z, t plus delta t minus alpha of x, y, z and t. We can find out this change by using the chain rule of differentials that you have already studied in the calculus, and by using that rule, this change is equal to partial alpha by partial x multiplied with the change in the value of x between these 2 points, that is equal to x plus delta x minus x, that is delta x plus similarly partial alpha by partial y delta y plus partial alpha by partial z delta z plus partial alpha by partial t delta t. Since these two changes are equal, therefore we can equate them. So after equating them, we have alpha of t plus delta t minus alpha of t is equal to partial alpha by partial x delta x plus partial alpha by partial y delta y plus partial alpha by partial z delta z plus partial alpha by partial t delta t. Next we will divide both sides by delta t, so we get alpha of t plus delta t minus alpha of t divided with delta t is equal to partial alpha by partial x delta x divided with delta t plus partial alpha by partial y delta y divided with delta t plus partial alpha by partial z delta z divided with delta t plus partial alpha divided with partial t. Now we will take the limit as delta t approaches to 0, then the left hand side is the total derivative of alpha with respect to time t, and it is equal to d alpha by dt. But here we will denote it by capital D alpha by capital dt. And note that in the Lagrangian description, alpha depends on the time t only. Therefore, if we differentiate this equation with respect to t, then we will get the total derivative of alpha with respect to time t. Therefore, this derivative is called the derivative in the Lagrangian coordinate system, and we call it the Lagrangian derivative or the material derivative, or it is also called the substantial derivative. The reason to call it the material derivative or the substantial derivative is because the Lagrangian coordinate system is also called the material or the substantial description, because we have to follow the motion of a piece of the matter, okay, that is the fluid element. Note also that in the limit delta t approaches to 0, this quantity becomes the total derivative of x with respect to time t, which is the x component of the velocity of the fluid, okay, and we will denote it by Vx. Similarly, in the limit delta t approaches to 0, this is the y component of the velocity, and similarly in the same limit, this quantity is the z component of the velocity of the fluid. So in the limit delta t approaches to 0, this equation becomes as the total derivative or the Lagrangian derivative of alpha is equal to Vx partial alpha by partial x plus Vy partial alpha by partial y plus Vz partial alpha by partial z plus partial alpha by partial t. Okay, note that the dot product of velocity with the gradient of alpha is equal to the dot product of Vx, Vy, Vz, this vector with partial alpha by partial x, partial alpha by partial y, and partial alpha by partial z. This dot product is equal to Vx partial alpha by partial x plus Vy partial alpha by partial y plus Vz partial alpha by partial z, which is equal to this term in this equation. So we can write this equation in more simplified form as d alpha by dt is equal to partial alpha by partial t plus the dot product of the velocity field v and the gradient of alpha. Okay, and this quantity can also be written as dot product of v and the gradient alpha. You can first evaluate this dot product and then you can apply the result on the property alpha. Okay, so therefore this equation can also be written as d alpha by dt is equal to partial alpha by partial t plus v dot the del operator applied on the property alpha. Now the left hand side is called the Lagrangian derivative of alpha, as we already know, and the whole right hand side is called the Eulerian derivative of alpha. So this is the equation that relates the derivatives in the Lagrangian coordinate system and the derivatives in the Eulerian coordinate system. Note that the Eulerian derivative has two terms, this one and this one. The first term is called the local derivative of alpha, and it expresses the fact that the value of alpha at a fixed point may change as a function of time. Okay, and this is the reason why it is called the local derivative of alpha. The second term is called the convective or advective derivative of alpha, and it expresses the fact that if the flow field is steady, that is the property alpha does not depend on time t and hence it vanishes, then there is still a change in the value of alpha due to the motion of the fluid. Okay, let me understand these two terms with the help of examples. In our first example, we will consider a cup of hot tea in which the tea is unstirred, that is, the tea is not moving. We have to calculate the rate of change of temperature of the tea. Note that the tea is not moving, therefore the velocity field of the flow is a null vector and hence the convective derivative of the temperature of the tea will vanish. But note that as the time passes, the tea cools down. It means that at the fixed points within the tea, the temperature will not remain constant. It will change as a function of time t. So the local derivative of the temperature will not vanish. So from this equation, the total derivative of temperature T is equal to the local derivative of the temperature. Since the T cools down, therefore this partial derivative is negative. This example expresses the fact that even the fluid is not moving, there is the change in the temperature with time t. Let me move to the second example. In the second example, consider the flow of water through a water heater. Suppose that at this point within the heater, the temperature is T1 and it does not depend on time T. Okay, that is for all time this temperature remains fixed, and same is the case for all of the other points within the heater. Now note that the flow is independent of time T, therefore the local derivative of the temperature will vanish. But as we move through the heater, then the temperature changes. Here is the temperature T1, and as we move further away from this point, then the temperature increases. Therefore the temperature is changing with the position, and hence the convective derivative term is non-zero because the gradient of the temperature is non-zero. Okay, hence in this case the rate of temperature is equal to the convective derivative term. Okay, note also that the velocity is non-zero because the water is flowing, and hence the velocity field is not zero. And as we move through this heater, then the temperature changes from point to point, and hence the gradient of the temperature is not zero, and hence the convective derivative of the temperature is not zero. Okay, so this is the required rate of change of temperature in this case. So this is all from our today's lecture. I hope that you have learned.